Right, good evening, everyone. A bit of housekeeping first. We're not expecting a fire alarm tonight, so if it goes off, it's real. And you need the toilets through them double doors and sort of straight ahead and right. And also, we're expecting some teas, coffees, and biscuits soon at some point, so just have yourself if you feel like it. So tonight's seminar is being presented by Paul Wilson, who's the founder of PMW Technologies, and I had the opportunity to do a placement with him early last year, and I know we're in for a very good seminar. So give him a warm welcome, please.
Very much, Ben, and welcome to you all. I'm pleased to be here tonight. Thank you very much, Theo, for the invitation, and Ben for doing all the organising here. Right, so we have some unexpected physics. I hope this isn't too unexpected and that we have an interesting session. Carbon capture. Why do we do it? Why do we even think of doing it? Well, starting point, ending point for a lot of this is minimising the carbon impacts on the climate change that we're suffering. That plants like the one on the right there at Stanlow tip out millions of tons of carbon dioxide a year and make a serious difference to the UK's contribution to climate change. So reducing that is only a good thing, and the sooner we can do it, the better. Technologies have been a real challenge moving forward with carbon capture. I'll talk a little about those, but also about what we've done and where we're going with our technology. So the intention here is to cut unavoidable carbon emissions. There are many industrial processes that don't just emit carbon dioxide because they burn fuel, but because of the chemistry of the processes that are involved. So brick making, ceramics, glass making, even oil refining, there's an unavoidable element of carbon emission from the processes being done. So no amount of hydrogen or renewable energy will replace those elements. You have to deal with them as carbon dioxide emissions. We also have a shorter term problem. By 2050, whatever will have happened. Between now and then, we've got a whole load of investments in existing plant, machinery, processes, industries that have a commercial value drawn from existing assets that emit carbon. And we can't simply switch off the fossil fuel. We have to move away from fossil fuel in a controlled way that doesn't destroy the economy on the route. So we have to have some means, and carbon capture is one of those bridging routes which will enable us to move from where we are now to a ideally zero carbon future. One of the key questions with carbon capture is, what do we do with the carbon dioxide? It's all very well saying, well, we can capture the carbon dioxide. Where does it go? What do we do with it? It's not just a simple problem that we can put it in a landfill site and forget about it. It's not that kind of stuff. So geological sequestration is the kind of classic solution and is already practiced in a number of countries around the world. The point here is that you are basically putting it away under the ground, ideally, and in many instances, in a position where the chemistry of the subsurface conditions will ultimately result in the carbon dioxide being fixed in the rock and will not come back. So that would happen certainly into saline aquifers, and salt caverns can do those kind of chemical things. Depleted oil reservoirs probably will hold the carbon dioxide in much the same way as they've held methane and the other hydrocarbon gases underground for hundreds of thousands, even millions of years. So disposal is one way of dealing with carbon capture. It's not ideal because there's always the chance of things coming back before reactions are complete. The questions of liability and ownership of the carbon dioxide under the ground. Who is to look after it? Who is to deal with it? Who is to pay for putting that stuff underground? There are options including mineralization. This is the famous slate lime plus carbon dioxide equals a precipitate of calcium carbonate. It's this kind of process. The favoured one is to use magnesium oxide or hydroxide minerals reacted with carbon dioxide to produce magnesium carbonate. So this is basically ground up rock absorbing carbon dioxide and chemically fixing it as a building material. So it basically makes a form of concrete or plaster that fixes the carbon dioxide in part of a mineral. And finally, you have the options and possibilities of reusing the carbon dioxide. It can go into food, beer, gaseous drinks. It can be used as a sterilizing agent. More usefully, it can be used in alternative plastics. And here's the picture of one of the routes into some of the components of polyurethane plastics, that you can actually substitute some parts of the chemistry with carbon dioxide. You can also create synthetic fuels from carbon dioxide. You can react carbon dioxide with hydrogen to produce methanol, or you can produce methane or other hydrocarbons with varying degrees of efficiency. One that we see is very attractive for a particular application is what we call the methanol cycle, which is where for shipping, and long haul shipping has difficulty carrying enough renewable energy about. Batteries simply aren't enough, and you can't really realistically carry around liquid hydrogen as your fuel produced from renewable energy. So forming another chemical compound is a preferable solution. And producing methanol from hydrogen can be done quite efficiently. Methanol is a liquid fuel. It's a bit like gasoline. It can be burnt in conventional engines, and you can capture the carbon dioxide on board ship using a process like ours to bring the carbon dioxide back for reuse with more hydrogen, so that you're effectively using using carbon dioxide as a carrier for hydrogen to deliver it on board ship. And that you can take your ship around the world with that. This certainly is of interest, and we're in discussion with a number of shipping fleet operators who are interested in the idea of this. If nothing else, because if they own the solar farm in Australia, they can produce their own hydrogen. They can recirculate the carbon dioxide on their own ships. They can become completely independent of anybody producing a fossil fuel. So they have complete control over their economics of shipping their product. So this is quite a valuable step forward, and it really moves carbon capture from being a rubbish processing operation for sequestration, effectively landfill, to being a recycling operation, a circular economy. So this is quite interesting, and that's certainly a prospect that is going forward. Let's look at some processes. The classic process is the so-called amine process. Amines are organic versions of ammonia that will react with carbon dioxide. So basically, you dissolve the carbon dioxide in this solution. To get the carbon dioxide back out again and regenerate your solution, you have to heat it. So it consumes a bunch of energy needed to recover it. So this picture here is the Boundary Dam demonstrator plant in Canada that cleans up the exhaust gases of a power station. It's a substantial piece of plant for a relatively small power station. Unfortunately, the amine solution is hazardous. You don't want to let it out in the environment. It's damaging to natural life. It's also, unfortunately, bad for human beings. So you don't really want to handle it either. But worse, the contaminants of the exhaust gases from combustion can often contain sulfur oxides, nitrogen oxides, and that degrades the amine. So you actually have to take a slipstream of amine off to clean it up or replace it with new, which means handling, it means more processing, more risks to the environment. One of the advantages of this process is that it is relatively straightforward to scale up. If you wanted one of these things larger than Boundary Dam, then it just happens to be a whole load, either more or bigger absorption columns, more heat required to recover the carbon dioxide. But fundamentally, it's a big chemical process, and you can manage that. An alternative process that's Widely used for natural gas processes is the membrane separation process. And this has a membrane that is selectively porous to carbon dioxide. Unfortunately, it requires a significant difference in pressure. So we have an energy requirement to compress particularly exhaust gases to do such separation. And it has limited selectivity, so it will achieve a reasonable separation in one stage, but generally requires multiple stages to get reasonable purity of carbon dioxide and an adequate level of removal, like 90%, from the existing gases. So energy intensive, and the limited permeability of the membrane means you have lots of them. So you have crates and crates of stacked up membranes, each membrane being a kind of bundle, cylindrical bundle in a pressure tube with the gases coming in on one side, separated gases coming out on the other. Quite a hefty process. And again, unfortunately, contaminants in our exhaust gases are very bad news, that they degrade the membrane so that over a number of years, the membrane becomes worn out and not so selective. So you have to invest in the expensive part of the process being replaced at intervals through life. So at the moment, this one is not really considered a suitable process for exhaust gas cleaning up. It does work relatively well with natural gas processing, where there is already pressure to drive the process, and removing, say, 80% of the carbon dioxide is enough for the purposes. And there are cryogenic processes. Ours is a cryogenic process, but the classic cryogenic process separates carbon dioxide by desublimation. It exploits the strange property of carbon dioxide that when you cool it at atmospheric pressure, it never condenses as a liquid, it goes straight to solid frost. So that means that you can run your cold box with heat exchanger, and you will frost up, just like you freeze up the inside of your refrigerator. It will frost up with carbon dioxide on the heat exchanger surface. And then all you do is you switch your heat exchanger to being warmed to melt the stuff or evaporate it off again, and you can recover your carbon dioxide. Unfortunately, the frost of carbon dioxide on the outside of the heat exchanger degrades performance, so you need extra large areas. And then because you're alternating melting and capturing, you need multiple sets of surface. So it's 3 times as much of expensive surface. So it makes it an expensive process. And the scale up becomes quite difficult because the sheer area of surface you require in your heat exchangers becomes unmanageable. So our process is also a cryogenic process. We use low temperatures again to capture the carbon dioxide as a solid. But rather than having a fixed heat exchanger, we use fine metallic beads. It could be ceramic or glass. But the beads act as an intermediary for the cold and capture the carbon dioxide. Overall, the process starts by quenching exhaust gases to a starting low temperature. Then we have a cooling stage that takes them down to about -100 degrees, which is just a straightforward regenerative heat exchanger, using the treated gases to recover the energy. Then we have a separation step where we cool things further to get the carbon dioxide separated. And we have a refrigeration process wrapped around this to provide the drive to keep the cold. Fundamental principle is here, that the vapor pressure of solid carbon dioxide descends very quickly with temperature. So you can see that from our typical 1/10 vapor pressure, 1/10 of a bar for 10% carbon dioxide content, exhaust gas typically, to get to less than 0.01% bar, which is down to 95% reduction, we only need a 22-degree change in temperature, which is really quite modest and is achievable relatively easily. And if you wanted to go to a much larger reduction, it's only another 5 or 6 degrees and you're down at 99%. We calculated that the energy penalty of going to 99.5% from 90% It's only 25% more energy to get there. Whereas the big chemical processes like amine will never get to 99.5% because the column would be hundreds of meters high to achieve an equilibrium over that chemistry. So the process is inherently rather attractive. The starting point is that we quench, as I said, and we use conventional equipment. It looks like a tank with water splashing down inside it. They can be recirculated, it can be once through. We put some additional cold in because we don't want too much water content of the gases at the end. So we try and get down to about 2 degrees centigrade. And because we're washing, literally, the gases, we take out particulates and sulfur oxides and some of the NOx. Then we have the separation stage. This is in 2 parts. We cool them first. That's in the box on the left-hand side there. That is our heat exchanger. It uses a moving bed heat exchanger because that gives very high efficiency heat exchange between the gases that are being warmed and the gases being cooled. In that process, because we're going down from roughly freezing point down to -100, the traces of water that remain, a few hundred parts per million in the gases, are frozen out onto the surface of those beads and ultimately depart with the exhaust gases. And the contaminants like nitrogen dioxide freeze out and again are released back into the exhaust gases. The other contaminant gases, nitric oxide, carbon monoxide, are present in too low a concentration to be affected by the cold processes. They simply stay as gases and pass through the process entirely unchanged. The critical stage on the right is where we cool further. So we cool by the 25 degrees or so I showed you before. And finally, having separated the carbon dioxide on the cold bed material, we warm the bed up to about -80, where the vapor pressure of carbon dioxide is atmospheric pressure, so that we can get the carbon dioxide out as a gas at the bottom corner there, and we compress it and liquefy it. So finally, the bed, the important intermediary, is lifted back to the top and goes around the cycle. So these use technology that's relatively commercially available. I've hacked about manufacturers' pictures to produce these images. They're on the web. Refrigeration is an important part of this process and is actually quite a vital part about how we minimize the energy. There are 2 different processes we can use. There's a conventional process called mixed refrigerant, where you have 2 different gases that condense at different temperatures and pressures. Or you can use a nitrogen cycle technology, which is like a gas turbine, except being used to produce cold rather than generate power from heat. We prefer the nitrogen cycle because it avoids flammable and difficult refrigerants because they're often either flammable or toxic or both for the conditions we're dealing with. And because we have the 2 processes, one of cooling to produce cold sufficient to freeze out the carbon dioxide, and then we're warming it subsequently to recover the carbon dioxide, a significant part of the refrigeration heat rejection is at low temperatures. So we have a very much reduced refrigeration power requirement. We have a remarkable result that we get something like a 60% reduction in the power demand for our refrigeration for the amount of cooling we require compared with a conventional process because of that heat rejection we're able to use. And because we're not going as cold as the liquid gas facilities that traditionally use the nitrogen cycle refrigeration, we can use air. So we don't even have to have a particularly clever makeup system for any leak of our refrigerant. It can leak, it's free. We don't want it to leak, it's cold. But if it does leak, and they always do, it's free to replace, which is wonderful. And again, that's an Air Liquide plant I've got a picture of. They're standard enough items. They're used already on board ships, for example, to re-liquefy vapor from liquid natural gas transport. Now, the carbon dioxide end we really have to have it as liquid, particularly for things like shipping. You can compress it and send it down a pipeline. For many applications, they're too small. You want to liquefy the carbon dioxide to carry it away. And our ships will have to have it liquid because there's no pipeline to a moving ship. So the advantage of the process is because it's working over that very small temperature range, it actually produces very high purity carbon dioxide. It's an inherent feature of the process. You actually crystallize the carbon dioxide. Crystallization is another classic purification process. So we have high purity CO2. There's nothing else there. There's no water, absolutely minimal traces of other stuff. That means that the traditional liquefaction processes for carbon dioxide, which spend most of their effort purifying, are avoided. So we have on the process a picture on the right there, all that brown stuff that's out of Linde's catalogue for carbon dioxide liquefaction. That's purification plant. That's not liquefaction. You don't need it. It's free. It comes pure to start with. So it's a very much simpler process. And that means reduces energy consumption. And we can use conventional bits without really making much of a song and dance about it. So we have the benefits of cryogenic separation with the small temperature differences, meaning we can do the job nicely and efficiently. It's easy to apply because it's highly selective, high purity, and it's safe. We have a moving bed, and our moving bed, because it's fine material, short paths for gas flow through the bed, we have very intense heat transfer. So it's small, compact, it's thin. We get, in our 100 millimeters typically of bed, we get the same separation as the chemical separation process gets in a 10-meter separation column. So we're, what's that, 1,000 times better? 100 times better. It's quite enough. And because we've got very large surface area to capture our carbon dioxide on, we don't suffer from the heat exchangers being frosted up. It's just too thin a layer to matter. And because we integrate the refrigeration, we have the low energy consumption because we're rejecting heat within the process at low temperatures. We have a nice straightforward refrigerant that is non-toxic and doesn't cost us anything to make up. And the gas cycle, unlike other refrigeration cycles, we're not dependent on the properties of the air, other than the fact that it doesn't freeze or it doesn't boil or condense. That process means that we have a very flexible plant. The refrigeration can be used for a wide range of carbon dioxide concentrations. So, the physics. I think we should have a break and have some tea, and then I'll tell you about the physics. How's that go? If anyone would like some tea or coffee, it has arrived at the back here now. So, right, so the challenging physics. Here we see the core of the process, which is where the core of the challenge comes. We've got a number of places where we have a significant issue, which is that the material that we use for heat transfer, the moving bed, is moving, and we can always have problems with how it moves. So achieving an even bed flow distribution through the process is rather vital. We have an interesting challenge of managing the heat transfer, because again, bed material, it's porous, it doesn't conduct heat wonderfully, but we've got to do our heat transfer. It's got to be efficient and effective. And a more complicated situation where we're actually doing the desublimation of carbon dioxide onto the beads, we've got to manage that heat and mass transfer and understand what's going on to scale that effectively. So, first degree of challenging physics. We have the bed flow problem. Or not. It won't flow that easily. Bed flow is a challenge and has been for a long time. The classic situation you end up with is no flow, because you get the material goes down the bottom and makes an arch. It just plugs up the bottom of the silo. The next form is that you can get what's called rat holing. It's a wonderful idea, but basically it goes down the middle and you don't get a uniform flow. So if you had a heat exchanger or gases injected in the across the width, only the middle bit would see moving bed, the rest would be static, useless. And only the right-hand side, which is something that's only really been understood, but unbelievably, for the last 60 years, is what's called mass flow, where the whole lot is moving gently together. It's only been for that length of time that people have been able to design silos to do that reliably. So all those power stations that we see, the coal-burning power stations, precede that time, and that they had forever problems with the mess of low-grade coal they were burning, clogging up, jamming their hoppers, which are just big silos. And they had air cannon to disturb it. They had sledgehammers to move it. It was not a problem that was well solved. So the leader in this was a man called Andrew Jenico. He was from Poland originally, and he went to America and worked on silos in the 50s, try and understand what was happening. And it wasn't until the 60s that he got enough experimental and theoretical work done to be able to design a silo for iron ore crushings that would work reliably. And what he had to do was relate the material properties and the silo wall and silo geometry. So on the right there, you see a picture of what he had drawn, which he had two different parameters. The wall friction angle, which is how easily the material flows down the wall, and then the hopper angle. Thank you very much. Thank you. I deserve this, I think. So he categorized the flows that he could get into the mass flow and funnel flow. Obviously, you don't want to be in the situation of having arches, so he was out. These are out with that region, and his angles were quite a lot shallower, much more steep than had been previously used to achieve a satisfactory behavior. And his shear tester allowed the material properties to be understood and being able to effectively rub the material against a sample of the wall to measure the wall friction factor, and to screw the material against itself to measure the internal friction forces between the material. So he defined those criteria, enabled science to move forward. And moving to predicting those behaviors from a theoretical point of view, outside the empirical measurement of those parameters, has proved very hard. It works at every scale, from the microscopic interaction of the particles, which can be powder or small beads, all the way up to quite large lumps. But it's within a silo that can be meters high, meters in diameter. So it becomes a very difficult problem of scaling, that the internal and external pressures within the silos are not obvious, and they have quite a strong effect on how the material sticks together. If it's a bit damp or finely divided, the material can stick together, agglomerate into a lump. It can be very difficult to handle. And so the large range of scale means that the phenomena are very hard to handle. And the modeling and analytical stuff is difficult. Discrete element modeling, which is a way of dealing with many particles, is really defeated by the fact that you're talking about 10 to the 9 particles. It's just going to take too long to do the computation. It has been done, and they do horrendous runs that take a fortnight to analyze behavior, but it's not really very rewarding, and it's not a particularly effective solution in the end. And you have multiple conditions within the silo, that you have sections of flow, perhaps in the outlet, where the material is so divided it's behaving more as a gas. You can have in the throat, it's actually flowing much more like a liquid. And in the sections higher up, where it reacts to the wall and in itself, they're much more behaving like a solid with internal friction processes going on. So the technologies of applying CFD and actually getting meaningful results from that are relatively recently developing towards the point where you can use this kinetic theory of granular flows, for example, to actually understand what's happening and to reflect the different modes of operation of the material. But all of this still has to be rooted in well-controlled physical experiments. It's not a simple matter of doing the sum and coming out with an answer. You have to actually check and can go back and forth to your models. The situations that we're looking at are much more sophisticated than merely the emptying of a silo, but they have the same issue that we have a silo. Whenever we put two heating plates together, we have a material flowing down a gap. This is a separate silo. How does it work with respect to adjacent channels? How do you merge them? What happens when we inject gases into them? Quite a tricky problem. The science is getting better. On the right there, you can see the experimental results from a physical model made in Perspex, traditional, foot wide, 3 feet high, with varying outlet geometries. And you can see for the different diameters and grams per second flow for the throat of the funnel. The hollow boxes are the experimental results. The black boxes in the red line, two different CFD theoretical results. So we're getting close to a believable model now, but we're talking about quite sophisticated application of this. We have some way to go. Heat transfer, it's always a good one. This is now quite a popular topic because the use of bed materials, for example, for solar energy capture, where you have solar towers reflecting the light up onto a heat receiver. If the heat receiver uses a stream of sand or ceramic material, you can get very good capture and your moving material doesn't melt, doesn't do anything disgraceful, and you can then transfer the heat to a thermodynamic cycle. So this has been analysed at some length, and you can see here the traditional solution is that you have slots through your heat exchanger through which the bed material flows, and you have a coolant channel with the coolant flowing in the opposite direction. Often people prefer to use things like supercritical carbon dioxide because you can get a very good gas cycle with that. But now you've got a very interesting range of behaviours that the particles fit to the wall differently than they fit to themselves in the middle. So you have a wall and bulk behaviour that are different. You have the problem that the interstitial gas is the main conductor, but the actual contact points of the beads doesn't make a huge difference, that the results are not always that encouraging. You've got movement so that you haven't got a consistent pattern of contacts. And you've got whatever bed flow distribution you get the friction down the sides. Are you going to get a nice uniform mass flow, or are you going to get some kind of funneling going on here? You can solve the problem analytically. I've done this. It's not straightforward, but it's doable. The famous partial differential heat equation. It's quite heavy-handed. You have to look at the right solution and see how it works. But you can use that to estimate the performance. And in fact, our estimates, when we look back at experimental results on our pilot rig, we're within a factor of 2 of the right answer from analytical. I think that was quite good going. Heat transfer is a terrible problem. Really difficult to predict what you're going to get. Now, the hero of heat transfer in moving beds, amongst other things, is Octave Liebenspiel, a brilliant man and loved by his students, sadly no longer with us. Outstanding chemical engineer, wrote a really renowned chemical reaction engineering textbook that's still in use widely. And he explored fluidized and packed bed behavior, because obviously how you do chemical reactions often involve those kind of circumstances. And this is from one of the doctoral theses he supervised that shows heat transfer, the Nusselt number, which is such an important non-dimensional number for heat transfer measurement on the left-hand side, versus his multiplier, which is the Peclet number times a couple of relationships, all to the 0.25, which is not unlike other relationships in heat transfer. But you can see that it actually works for a wide range of materials, from cork through to copper, zirconia, polythene, and silica. And the relationships there for performance of the heat exchange are remarkably good. And it really made it possible for us, for example, to estimate what we might expect from a heat exchanger. And I'm sure it's informed the design of the physical things now. Then the next one, heat and mass transfer and desublimation. Well, as I said, we have small particles, so we get short turbulent gas paths, we get the millimeter scale beads, high surface area per unit volume. So we have intensive heat transfer. The temperature changes, as we can see on the right. It goes from the bottom where it's warmest to the top where it's coldest, only about 25 degrees. And as the bed falls and the gases flow up, the carbon dioxide is deposited as a layer on the bed material to be carried out downwards. So quite a complex set of processes going on here. What we did, looking at this, is that we thought, right, we need to have an empirical evaluation of the heat transfer coefficient. We can't actually work out what the implications of the carbon dioxide will be, but let's look at the measurements and calculations of others. And that gives the top equation, was the first one that we thought was a credible value for the heat transfer coefficient. And then a similar thing from work done by KTA, who were the German nuclear research group, who were looking at pebble bed nuclear reactors, where you have golf ball or tennis ball sized lumps of graphite deposited around a core of uranium oxide, which is the nuclear part. And those balls would simply be heaped up in a column tube under helium at high pressure, and the nuclear reaction would heat the helium being blown through the bed. So they did a great deal of evaluation of pressure drop to work out what was happening would happen in their reactor. And so that approximation, empirical data on the right, those equations, which unlike pressure drop down pipes and things that you see. And we then said, well, let's just analyze what happens. We have a variety, what is the range of bead diameters that would be reasonable? So we chose 2 millimeters to 10 millimeters. Let's see what happens. And what we calculated was for a constant pressure drop through a bed of those beads, we had nearly identical heat transfer coefficient. And so what have we done wrong? How is this happening? What magic is going on here? Why are we getting a constant heat transfer coefficient for that level of flow? What's happening? And we had to go back to the great master of fluid dynamics, fluid mechanics, Osbert Reynolds, who was early academic, one of the first professors of engineering appointed in the UK. He was appointed to Owens College, that's now part of Manchester University, and he established the key laws of fluid dynamics, doing famous demonstrations of the laminar, transitional, and turbulent flow of fluids in pipes. He had a famous rig that he took around to show people with his glass tube, and he injected dye into the center, and at low flows the dye would remain as a line down the middle, and as the turbulence went up with the flow, it would break down at one point or another down the tube with turbulence, demonstrating the thing. And he created this dimensionless measure, the famous Reynolds number, that measured the difference in properties of the fluids, so that you could compare different fluids in different operating conditions and predict when they would be turbulent and when they would flow in a laminar manner. And he had very wide interest, much wider than that alone, to look at the mechanical and thermodynamic behavior of fluids and heat transfer. And he came up with an analogy. He said that the processes of heat transfer, mass transfer, and pressure drop were all related to the same mechanism. You imagine quanta of material effectively being transferred across a gradient of velocity, temperature, or concentration, so that they were delivering a chunk of momentum, in other words, pressure drop, to the wall, or they were dumping a load of mass to the wall because of the concentration gradient. And so he predicted that the heat transfer coefficient would be the same for a constant pressure drop down a pipe. We haven't got a pipe, we've got a bed, but it does it. It's nearly exactly the same heat transfer coefficient over a wide range of bed sizes. So with the very short turbulent paths, the high heat transfer coefficients we're getting, we've actually got a very real application where Reynolds analogy works. In most real applications, it doesn't. And many famous physicists and engineers have come up with improvements on his analogy to better predict. But we got one that works straight away. Now, our challenges aren't finished. As I said, the modeling and understanding of bed flow through the system is a real challenge. Measurement of the local bed movement rates and the measurement of how much carbon dioxide we got on a particular chunk of bed material are very difficult things to measure. Today we were experimenting with a bed movement detector that would actually sense the passing of the individual beads as they move down our rig. It's partially successful, but there's a lot of work to be done to make one of those go, because you're dealing with particles of the order of 0.5 millimeter in diameter, and you want to measure a movement of a few millimeters, less than a few millimeters per second of passing a particular point in the rig. Quite demanding. We've got another complicated problem to do with heat transfer in the lower section of our process, where we're actually warming the bed. The carbon dioxide has been deposited on those beads. So then you're in a situation, you're warming that. What happens? Near the wall, you're raising the temperature. So some of that carbon dioxide is going to evaporate and condense in the bulk. So we're complicating the difficulty we have already with wall to bulk by the fact that we've now got carbon dioxide evaporating and diffusing into the bulk and condensing again, and desubliming again. So how does that affect the heat transfer? Our primitive assessment says it's about a factor of 3 better as a result of that phenomenon. But it's not yet clear that that's what the limit is. And we have a very sophisticated process here with a variety of things going on, and controlling that process to minimize energy use and maintain conditions appropriate to desublimation with a varying carbon dioxide content and a varying flow of exhaust gases. Very few industrial processes sit absolutely steady for days on end. You know, put it on board a ship and it's coming and going. When you're going to port, you have to handle it. So quite an interesting challenge to manage that manufacturing, that operation. So, we do exploit unusual physics. We have to understand it and make it work. We've had to cast our net wide to work out where and what will guide us. We've also had to work out some of our own solutions, not all of which have worked. And the work is now by no means finished. We've got a lot to do before this is going to be fully commercial. We'd love to have one of these things working in a couple of years' time at scale, and it may happen. We've got interesting discussions going on. So that's my story. Thank you very much. I'll be very interested to ask questions from the audience here or for those online. Thank you.
Are there any questions? Well, we have one question from the audience online.
Okay, I'll be happy to answer that.
Alexander was asking, why does the ship methanol cycle still leaks up to 5% of carbon dioxide?
Why does it leak it?
Yes.
Right. There is an obvious economic trade-off with the the carbon capture process, that you can take out 99.5% of the carbon dioxide from the exhaust gases at a penalty of burning more fuel to provide the power for the refrigeration. So there's a trade-off to be made of how much of the carbon dioxide is the right amount to take out economically. You can go to extremes, as I said, or you can go to a less extreme value. The cost is in replacing that lost carbon dioxide, and it must be replaced by non-fossil carbon dioxide. So this would be from biogenic sources, separated from biogas, for example, from digestion or combustion of biological waste materials. Energy from waste plants often burn the organic residues of food, for example, and those would be considered to be biogenic. But there's only a finite amount of them, so there's a trade-off how much of that carbon dioxide you can feed back into your marine cycle. But it's a fairly fine choice.
Thank you. There's a follow-up question from Alexander. How likely is it that you'll be able to deploy in 2 years? What interest do you have from industry?
2 years is probably a bit fast, depending what we mean by deploy. We could have a prototype system working on perhaps a megawatt of ship engine operational in 2 years' time. I think beyond that time scale, we would expect to be doing much larger scale and multiple applications. So we're looking at both shore-based and marine applications at that sort of scale.
Thank you very much. I actually have one question.
There's a question behind you.
So I was just sort of wondering, how much of an impact do you kind of see this having on, reducing the impacts compared to like current carbon capture tech?
Well, what we see is that current carbon capture technology is unlikely to be able to tackle things like the marine application, because the impact of the extra heat you require for driving the amines mean that you nearly double the fuel consumption on board ship to capture it using amines. So we expect there to be a significant take-up in the deep sea shipping, and that represents perhaps 2 to 3% of global carbon emissions. Then industry, the big industries, can be handled by amine processes, and they're probably relatively amenable to the limitations there. They can manage those. But there's an awful lot of industry that's at a different scale, that the scale of brick making, the scale of glass making is probably too small for those processes to be cost effective. And we see those markets, which represent perhaps a third of the industrial emissions, which may represent 10% of UK emissions, for example, would be appropriate to the kind of technology we're talking about. So we're talking about ultimately quite large potential globally.
One more question. What interest do you have from industry?
We've had interesting studies. We've talked to a food manufacturer, and the timing was bad, that they were very interested because they use quite a significant amount of carbon dioxide, and they have their own combined heat and power plant. They're burning gas to generate power and heat for their process. So they could capture their own carbon dioxide and substitute that for the process use. But just at the right moment, wrong moment, somebody invaded Ukraine, and the gas price globally went off scale, with the result that the company had much greater problems to do with the cost of its fuel than the cost of its carbon dioxide. So those discussions came to an end. We've done an interesting study for Tate & Lyle sugar, looking at application of the process to the sugar process, which is fairly energy intensive because you're recrystallizing sugar from raw cane to produce the high grade cane product or syrups they produce. And doing that process, capturing carbon dioxide is an option for decarbonizing those kind of plants. So there's There's not insignificant interest. It's not a primary target because it's very scattered, whereas shipping is relatively clearly one thing or another.
There's one more online. What's your biggest hurdle ahead?
Biggest hurdle. Getting the money to do the next step. When we're talking about several £1 million, it's quite a hard slog to build a team and prove to those with the money that this is actually going to happen and work. We're confident, we've seen it, it does work. Translating ambition and even technical success into a commercial success is an argument and discussion of its own.
Any further questions? So how long have you been working on this area?
Well, the concept, the very initial concept, the realization that you could combine the reverse Brayton cycle to produce cold and the use of a pebble bed to transfer the cold as an intermediate to carbon capture applications. That idea we applied patents for in 2016. And we got funding to do feasibility studies that started in 2017 when George joined me. So we've been working on it solidly since 2017.
Okay, good.
So we've done 5 good years so far, and another 5 years we should have it in commercial operation.
No,
That's how it goes. It seems 10 years seems to be gestation period for these kind of ideas.
Great. Would you like to show us a few things about how the rig looks like?
Certainly, I can show you a little about the rig. So our pilot rig, it's a big structure. Here's George perilously at the top, servicing part of the equipment. We have a test diesel engine. We have the pack columns here. They're 125mm columns packed with commercial packing. First water stage and the second one, chilled water. We use a high quality beer chiller to produce cold water. We don't drink the result. We have a moving bed heat exchanger here, the first interactive heat exchange. And you can see at the bottom, we put the wash gases in and take them out again cold. At the top, we've got cold gases going in and then vent gas going out. And there's the conveyor that rotates the bed material around. The column itself, which is all wrapped up in 3 layers of insulated polyurethane insulation. Top is the bed cooler, and that's the entrails. It's quite a thin thing, but it's a plate heat exchanger with bed flowing between pairs of plates between which compressed air flows, cold. We have a desublimer, which is just a box through which the gases flow and the bed flows the opposite way. And the bed warmer sublimer, which is a lovely thing made of plates. I think Dirash had a go at this one. And the metal plates are all fixed in a box, and they do the electrical heating to warm the bed to get the carbon dioxide out. And that comes out at the very bottom of the column there. Then we have our cold source, which is the liquid nitrogen dewar. We condense the air and mix condensed air back in with a venturi. Quite a fierce piece of rig design, really, and it's been very interesting to learn how to drive it and make it work. But it does get very cold. And then we have an ejector that recirculates the air, compressed air around. We have 3 flexible conveyors. One we've seen before for the cooler dryer, and 2 others for the separator. It makes a kind of D shape, so we lift in 45-degree steps. And here's some cooling. So this is when we cooled the rig as far as we could get it to go. You see the coldest line is the cold gas going into the heat exchanger from the dewar. And those spikes and lumps are because it's actually quite hard to manage. You have to keep topping it up with liquid nitrogen to the right level, not too much, not too little. And then finally, the tail end of that, we run out, because that's what happens. You never have enough liquid nitrogen. And this one, where we cooled the whole rig down, so many of the traces are all going down in temperature as we drive the temperature down. That run didn't get quite cold enough, but we did get down. The coldest was minus 110, and the process zone, which is the yellow and black dots, which are second to the bottom. Those are down at the -90 to -100, almost cold enough to do desublimation. And once again, the green spike going up at the end is run out of liquid nitrogen. Oh yeah, that's what we've been doing. I haven't got any more pictures of exciting things on here, but the runs are very interesting to do, should we say. The liquid nitrogen being steaming across our feet.
Sounds good. Any final question? Do you offer any placements to students?
We have done, yes.
Yeah.
Ben and Diraj were on the team last year. We're not quite sure what's happening this year because we're having to relocate from our present workshop laboratory space. So where we'll be in April is not quite clear. We're hoping to be moving somewhere elsewhere on the Thornton site.
If there aren't any further questions, let's thank our speaker again. Thank you very much.
Thank you.